cross-entropy is a widely used loss function, especially in classification tasks. It measures the distance between two probability distributions. Loss in common measures how different the true labels from the model's prediction. Consider two binary vectors where binary means the vectors have two possible values 0 and 1. If we have two vectors, vector y with true labels and vector y hat with the predicted labels, the loss function provides a universal measure of the difference between these vectors. This is the general purpose of any loss function and the role of binary cross-entropy in particular. The cross-entropy might look complex, but once we break it down, each part becomes clear and manageable. Let's begin with the foundation, the logarithmic function. To understand cross-entropy, let's first recall the concept of the log function. And in simple terms, the log answers the question: to what power c should we raise the base a to obtain the value b? And these two expressions absolutely equivalent. You can see that we raise the base a to power c to get b, yeah? And right over here we have a in the base of the log function, c as the result of the log function, and b inside the argument of the log function. Okay, let's check this interactive log plot. And we define the plotting function. Inside we generate a range of probabilities as the values x and compute the log values as the value y, as the variable y. Then we plot curve x against y and plot a vertical lines that just mark a path to x and y axis. And it looks like this. You can take the value between 0.01 and 0.99. And we have two scenarios. For high probability predictions that closer to 1, we have a logarithmic value that is closer to 0. You can see that, for example, when we install 0.6, it's negative 0.51. If we install, let's say, 0.8, it's for 0.82, it equals 0.2, and closer we go to the 1, closer we go to the 0 for the log. And for the low probability predictions closer to 0, we will result in highly negative log values. Let's say that we install 0.28, and we have negative 1.27, and closer we go to the 0, you can see that more and more extreme negative value we obtain from the log function. And it's much more extreme slope in the negative direction than in the positive direction. And this plot illustrates the behavior of the logarithmic function in two regions. Low probabilities area, it's just below this threshold 0.5, and high probabilities, that is higher than this threshold. This subplot zoom in on the low probability region between, let's say, 0.01 to 0.5, and this area just where the log function steeply declines. We have very steep decline, and we have a very high penalty for the values that closer to 0. And this subplot just focuses on high probabilities, where the slope of the log function just much more flattens, yeah. And you can see that for the low predicted probabilities we have very high penalty, but for the higher probabilities our penalty less and less steep every step towards the value 1. And here we have the binary cross-entropy formula. Binary, it means that we have only two classes, 1 and 0, for example, or let's say presence or the absence of something on the picture. So on this formula, yi is the true label of for the i's sample and can be either 1 or 0. The model predicts Pi, the predicted probability for the i's sample. It's the model's output, typically a value between 0 and 1. N represents the number of samples in the dataset or batch. The loss is averaged over all samples, and we divide the sum result by the n value. Now let's break down the logarithmic terms. Since yi can be either 0 or 1, this expression inside the sum notation activates only one of the term depending on the value of yi. And for the first term, it active when y equals 1, yeah, because in case of 0, 0 times the log of pi equals 0, yeah, we just destroy this term. It evaluates the predicted probability for the true class, for the class with the label equals 1. A high pi that close to 1 results in a small penalty, while a low pi close to 0 leads to a large penalty. We can easily reproduce it on our plot. So you can see that for very small value x, we have very high negative value for the log function, and when we go to 1, pretty close to 1, yeah, when x equals 0.99, we have negative 0.01. It's very small penalty. And this first term just amplifies errors for low probabilities, encouraging confident and correct predictions, yeah? Because we need to predict, in this case, that our probability must be 1 or pretty close to 1. And the second term, 1 minus yi times the log 1 minus pi, active when yi equals 0, because we inverse in some sense this value, yeah? When it equals 0, we just amplify this second term, we make it active, yeah, because it equals 1 times the log 1 minus this probability. A low pi that close to 0 keeps penalty small, because when we pretty close to 0, this body of this expression, yeah, of this log, pretty close to 1, yeah, because 1 minus the value that is pretty close to 0 just gives us 1. And while a high pi that close to 1 results in a large penalty, the logarithm again amplifies error for high probabilities and penalizing confident but incorrect predictions, yeah, by the same way as before, yeah. For very low probability we have very high logarithmic penalty. For very high, that is pretty close to 1, we have very small logarithmic function penalty. And last detail, it's this, yeah, right over here, we have this minus sign. Just because our log function always in the negative range, yeah, when we put the x in range between 0 and 1, we always return the negative value for the log function. And we just invert right over here for the binary cross entropy, this negative to the positive, yeah, just multiply to the -1. Now let's implement the binary cross entropy, and we need to import numpy as numpy. We create a class BCE and define method forward, just to follow approximately the same API as in PyTorch. So as the first parameter we have self, then we have predicted values. We can mark it as numpy and the array, target with the same data type, numpy and the array, and I think that we will return the same numpy and the array, yeah? So we return just the numpy list. Okay, in our formula, here we have yi as the target, as the data from our data set, yeah? And let's follow the same logic, yeah? We need to multiply target times the log of course, numpy dot log of predicted values, and we need to add 1 minus target, yeah, we implement the second term, times the log 1 minus predicted, and we need to add this minus sign to the whole expression. Okay, and let's create a variable loss, and then we return this loss value. I want to plot the binary cross entropy, and that is the reason why I just didn't divide it to n, because I just want to plot every point in the space, yeah, I just don't want to have one universal metric. If we want to have the real loss, we need to divide everything by the number of parameters. We can easily make it with numpy dot mean, and it will be absolutely the same result, yeah, as in our original formula, yeah. We just divide everything by the number of items inside our loss. When we work with the division or with the functions like log, we always need to remember about a potential trouble. When we reach 0, log return minus infinity, yeah? I think that in this case we can prevent this behavior. We can add one more parameter, epsilon, and let's make it by default as the 1e to the -7 power, yeah, pretty small value. And let's mark it as the float data type. Okay, we can add to this prediction this very small, very tiny value epsilon, and right over here for the second log call. In this case, even if our prediction will be 0, yeah, we just add very tiny value and prevent this unexpected behavior, yeah, that will broke our function. The best way to understand how cross-entropy works is to visualize it. Let's build the widely known plot with crossing lines that represents the binary case with two classes. First, we need to create an instance of the binary cross-entropy. Let's call the binary cross-entropy class, and we have this instance cross-entropy. We have two parameters in the forward, predicted values and target values. Let's generate y predicted. And for the predicted values, we just call the numpy linspace. Let's start from 0.001 to 0.999 and generate 500 items. We just build all of the possible probabilities that our model can return. So as the step number 2, we need to create two types of targets, because we have binary case. It means that target can be 0 or 1. Let's create the y target for 0, and we can call numpy dot zeros like and put y predicted to the argument, and y target 1 and call numpy dot ones like and put y predicted right over here. In this case, we create all the possible predictions, that just lean space, and then build target with full set of zeros and target with full set of ones. And we need to compute, or we need to just run cross entropy for the full set of 0, and we need to call cross entropy dot forward and put right over here as the first item y predicted, as the second item y target 0, and same for the full set of ones. So right now we put to the cross entropy all the possible predictions, and as the target in first scenario we just put the full set of 0. So it means that we just wanted to check at every point of the possible predictions how it behaves against this target 0. I just built this plotting code, we built a figure, visualize y predicted against the cross entropy for class 0 and y predicted against the class cross entropy for class 1. So it looks like this, finally. We have two lines, one line just blue line, and you can see that we started from very high loss, it goes straight to, I don't know, straight to infinity probably, and then it goes down, it's decreasing very fast, and after some point we just started to be pretty close to 0. So it means that when we have a class 1 and our probability returns value pretty close to 0, we have a very high penalty term, with our logarithm. And absolutely opposite, we just have this cross picture, absolutely opposite behavior for the red line. We have a very small penalty from the beginning, very low loss for class 0, and when our predictions is pretty close to 0. And then when our probability just starting to increasing, we have higher and higher loss, and higher penalty. So it means that pretty close to true class we have a very small penalty, but when we just totally wrong, at this point we should, for the blue line, we should predict 1, but when our probability equals pretty close to 0, we have this high penalty rate, and it looks like a cross, You can find the link to this code under the video and play with this by your own. When you train a model, you need to go to the backward mode in the gradient direction. When you follow the gradient direction, you need to track the derivative for all of the nodes of your neural network. And that is the reason why it's probably useful to compute the derivative of the cross entropy. And you can see how it looks, when we compute the cross entropy in the forward mode, we need to divide everything by the number of items in the batch or in the dataset. This over n step, 1 over n multiplier in the binary cross-entropy formula. But when you in the backward mode, you don't need to do this multiplication. You need to track every item separately, and you shouldn't average the gradient across your batch or across your dataset. So you can see that the key is inside the log derivative, yeah, and we remember that the derivative of the log function with respect to x is equals 1 over the x. So, and it's very easy to compute the derivative of the binary cross-entropy. Yeah, we just divide y at the i's point and divide it to pi, because we compute the derivative, partial derivative with respect to pi's term. And same works for the second term, yeah, but instead of 1 over x, we have 1 minus pi term. And when we expanding and simplifying, it looks like this. So, long story short, yeah, I already programmed this equation, yeah. We have predicted and target parameters as before and epsilon. So, and you can see that we divide right over here our prediction minus target over the predictions times 1 minus predictions. And in case if the denominator equals 0, it won't work fine, yeah, we just broke our equation, and that is the reason why we add this small epsilon term. Okay, and if you want to use your binary cross-entropy as the loss function, you need to call the numpy mean for your computed loss. Yeah, you need to average the loss over the batch size or the dataset size. Yeah, it's very important because you return just only one value that presents some universal measure of the accuracy of your model. But for the backward stage, you should not average the gradients. Instead, you should return the gradient for each example, as gradients represent how much the loss changes with respect to each individual predictions, and you just return the gradient as it is. Cross-entropy is a powerful tool in classification tasks. Logarithmic function amplifies the loss for wrong predictions made with high certainty and helping model learn more effectively.